Welcome to DP Tutorials by Donny Jarua. Now we will be highlighting and pondering upon another topic from electrostatics entitled Electrostatic Potential Energy of an Electric Dipole Placed in a Uniform Electric Field. Now let us emphasize about an electric dipole. Now, an electric dipole, as we already know, that is a system of charges bounded by two equal unlike charges separated by a finite distance between them. We have dealt this particular derivation that when you place an electric dipole in a system of uniform electric field, that means this electric dipole will experience what? Will experience a torque. So, like for instance, if I have an electric dipole, okay, if I have an electric dipole in this form, one charge is minus q and the other charge is plus q. And when you place this in a system of in a uniform electric field, what will happen? That means it will experience. This is your field lines, direction of the field lines. So what will happen? It will experience a torque. So we have learned that the torque experienced by this dipole is given by certain equations. Also, let me reiterate on some of the key points that what will happen to an electric dipole when you place in uniform electric field. It experiences a torque, and some of the force experienced by the respective charges will be in the opposite direction, where F1 will be the force on plus Q and F2 will be the force on charge minus Q. Likewise, there will be force, and this force will be and then this force will be equal to F equal Q into E. Those are the things that we have learned. And after derivation, we know that torque is nothing but the product of force into that perpendicular distance. Okay, perpendicular distance. So tau, after derivation, we got the equation of tau equal PE sine of theta, where theta is the angle between the direction of our electric dipole moment. Okay, electric dipole moment. So these are the key features. Okay, these are the key features for understanding the concept pertaining to an electric dipole. So now we will find out what is the potential energy. Now, brief idea about what is your potential energy. When I talk about potential energy, is nothing but the energy which is stored. Okay? The energy which is stored on any system. Okay? The energy which is stored on a system. Okay? Energy which is stored on a system by virtue of its configuration. Okay? By virtue of its configuration. Now, when we talk about configuration, it might be change in shape, change in size. Okay? All those is your configuration. So from here, if we rotate the dipole from one point to the other point, that is the meaning of what? Potential energy. Potential energy in physics, okay, there are various types of potential energy. You will learn there will be what we define as the gravitational potential energy, number one. Okay. Number two, we have what? We have learned in class 11 about elastic potential energy. Okay. There is also elastic potential energy. And now, in this particular topic, we'll be learning about another important point, which is known as your what? Electrostatic potential energy. So these are the three types of potential energy that you will be learning in this +2 stage. Okay, so you have learned about this, you have also learned about this. So now we will learn in details about what is this electrostatic potential energy. Okay, so now when you have this electric dipole and when you place this electric dipole on a uniform electric field, then what will happen? It will experience a torque. Okay, it will experience a torque. And let us place this electric dipole consisting of charge minus q and plus q, and which is placed in uniform electric field E. Okay, it is placed in uniform electric field E, and we know that the direction of the dipole moment will always be taken from the minus charge to the plus charge. So this will be the direction of what? This will be the direction of our electric dipole moment. And in this case, we find out that the direction of this P vector is at a certain angle with respect to the electric field vector. So P and E are inclined at a certain angle, which means that over here, if this is our dipole moment vector and if this is our electric field vector, then there is an angle which is subtended, between the electric dipole moment vector and the electric field vector. So from here, there will be torque. So there will be rotation. In this case, we expect that there will be a rotation. A rotation will be 1. The rotation of the dipole will be at the center or O of the dipole. This is the center O of the dipole. So we expect that there will be rotation. So there will be rotation. When it rotates, that means it rotates. It will be pivoted. Okay, the rotation will be in the counterclockwise direction. Okay, the rotation will be in the clockwise direction and this center also it will rotate. Okay, so if this is your dipole and if this is the axis passing to the center O of the dipole, this will be charge minus Q, this will be charge plus Q. So this dipole will rotate in that direction. Okay, so this dipole will rotate along that direction. Now, when the dipole is held, that means it experiences a torque, and this torque is given by that formula tau. Okay, is given by that formula tau equal PE, okay, sine of theta. Now I have to describe about what is this theta. Theta is the angle between the dipole moment and the field direction. Now let us put an assumption that if you rotate this dipole through a certain angle, okay, if you rotate that dipole through a certain angle, what will happen? See, if you rotate this electric dipole through a certain angle, suppose it is being rotated through a certain angle. Say if it is this is your dipole and let that dipole be rotated. Okay, let that dipole be rotated to a certain angle. That means this is the phenomenon in which it is being rotated. Okay, this is the phenomenon in which it is being rotated. Either this angle will be large or this angle will be small. So that is the way in which it is being rotated. Okay, so that is the angle. Okay, this is your angle. This is your angle. Now, when it gets rotated, suppose to an angle of 90 degree. Okay, when it gets rotated to an angle of 90 degree, this vector, that means it will be rotated in this way through various angles. Okay, through various angles. So let us rotate this vector through a small angle. Okay, let me rotate this vector and rotate dipole moment to a small angle. So in this case, let from this angle theta, let me rotate this angle to a small angle. Okay, to a small angle. This small angle over here, that will be d theta. Okay, d theta. So from theta, it is being displaced to an angle of d theta. What will happen? So in order to rotate from this old position, then this is defined as well as the original position, and then when you rotate to this new position, so what will happen? There will be the change in our configuration. So when there is change in our configuration, what do you have to do in order to rotate from original point to the new point? So what do you have to do? You have to do in physics, when you move something, that means there should be work done associated with that object. So this work done which is associated with that object will account for energy storing. That means there will be some energy which is stored on the system. Then this energy which is stored in the system will be in the form of PE. Okay? This energy which is stored in the system will be in the form of what? Will be in the form of PE. So all those are the important characteristics. Okay, say over here. So when you rotate this vector, so when you rotate this electric dipole to a small angle, that means you have to do some work. Okay, so what will happen? Over here I've written when you rotate to a small angle. Okay, when you rotate to a small angle, what will happen? Then work done in doing so is given by what? So the work done, let dw, okay, let dw be that small amount of work done. Work done is what? What is the working formula for work done? You should know. You know what is the working formula for work done? Work done is nothing but force into displacement. Okay, force into displacement. So W equal force into displacement. Over here, what type of displacement? The displacement in this case will be angular displacement. Okay, in this case, it is not linear displacement. The displacement in this case is one. It is our angular displacement related to one, related to that small change. Okay, related to that small change over here, d theta. So that d theta is our angular. That d theta is our one. Is our angular displacement. Okay, and this force, what is this force? This force is that torque, because I have explained to you. This force is that torque, rotational force, and it is what? It is your tau. So these are the key ideas that we need to know about the work done. Okay. So now let us move on. So what is your force? Force is not linear force. It is a rotational force. Okay. It is our rotational force. Then we can write this dw equal torque. So what is the work done? Work done is force. What type of force? Rotation force. Rotation force is tau. And what is the displacement? Displacement is your angular displacement. So we will write d theta. So what is tau? Tau, we can mark this as equation number 1. Then from here we can write this as PE, okay, sine of theta d theta. Okay, we can mark this as equation number 2. Okay, so now let us find the total work done in rotating from angles theta 1 to angles theta 2. Say, like for example, when we have a dipole in this form, this is our electric dipole. We have charge minus q, we have charge plus q, okay, we have charge plus q, and from here, this is the direction of our field lines. This is the direction of our field lines. All these will be what? All these will be our field lines E. Then next, suppose this angle made by that the angle made by that P vector with respect to E is theta 1. Then you want to rotate this dipole to a new position. Suppose let us rotate this dipole to our new position. Let that be the new position. From here, this charge gets displaced to that point. Okay, and then from here again, if I want to find out the direction between the theta 1 and the new position, okay, to theta 2, then what you have to do? That means at this particular point again, we have to draw the direction of the original field vector. Then what will be this angle? This angle, this will be one. This will be that angle. This will be that angle. That means this new angle will be theta 2. This is one. This is your theta 1. From theta 1 to theta 2. So what do you have to do? So rotating the dipole from angle theta 1 to theta 2, it is obtained by doing what? In physics, we have to obtain by integrating this equation 2. So we will integrate those equation 2. We will integrate, we'll use this integral sign, integrating from theta 1 to theta 2, we have, that means of that one, we are integrating that small work. And in this case, integration will be from what? From theta 1 to theta 2. Then from here you have to write, putting this value from equation 2, then we have that equation. We have this equation. Then from here, it is evident that the P and the E are one. This value of P and this value of E is constant for a given dipole. So we can take that P and E outside of the integral sign. Then we are left with what? We are left with integration of what? Integration of sine of theta d theta. But integration of sine theta is equal to what? Minus cos of theta. Okay, so implies that W will be equal to what? PE Then integration of sine of theta will give us what? Minus cos of theta. With the limits of integration going from theta 1 to theta 2. So from here, we can take this minus sign outside. Then we have cos. We can write in this form also, theta 1 to theta 2, theta 1 to theta 2. Then from here, it implies that this W, this implies that W, that means this will be minus PE. So from the rules, it says upper limit, we will put cos. First it will be upper limit, then lower limit, cos theta 2 minus cos of 1, cos of theta 1. Then after you solve, when you multiply this negative sign inside the bracket, yeah, you will get an expression in this form. Suppose we will write this as PE, then minus into minus will give us what? Will give plus. So cos of theta 1 will be in the front, and then minus into plus will give a minus into plus will give us minus. So that will change into what? That will be negative. So we will write this expression. This is our reduced expression. Okay, that will be our reduced expression. So we will mark this. Okay, we will mark this as the equation number 4. Okay, as equation number 4. So this work done, it is always stored on the system as well as its potential energy. Okay, always remember that work done is stored on the system as well as its potential energy. So in physics, we used to represent this potential energy by the letter 1. This W will be denoted by what? By the letter U. So this U will take the value of 1. PE cos of theta 1 minus theta 2. So this is the working formula. Okay, that is your working formula. So this is our working formula for the electrostatic potential energy experienced by the dipole. So up to this stage, it will be very important for preferably a 3 marks question in NBOS examination. Then